In this video, I'm going to solve another problem on Ampere's law. The problem is copied here. Let us go through it. In cylindrical coordinate system, so the coordinate system is cylindrical, the variables are rho, phi, z. H is given. H has only 5 component. So the solution part, we shall note down the components of H. R component doesn't exist. 0, 5 component, 4 rho minus 2 rho square. It is present. Z component also does not exist. There is only one unit vector, a cap phi. So rho varies from 0 to 1. Here it is mentioned meter, so everything can be taken in terms of meter. So we have to find rho, J, current density. We have to find current density, that is J, which is given by curl H, that is point form of Ampere's law. So afterwards you have to find current I from J. So I is given by surface integral of J over a surface S. So what is this surface S? If you read the question, the current passes through the surface Z equal to 0. So there is a surface at Z equal to 0. So here is the surface located. Radius varies from 0 to 1. Radius means it is a circle. So the surface becomes circular surface because of the radius 0 to 1 meter. And it is acting in Z direction, so perpendicular to Z axis. So this is what is the nature of the surface. And we can write an equation for this ds here itself. That is ds is equal to, the direction of ds is a cap z. So among the 3 variables, z is fixed for the direction. So the remaining 2, that is r and phi, become variables. One r will be there always. So this is going to be your differential surface area on this. So with this information, first we shall go for calculation of current density J from del cross H. Del cross H can be evaluated using the determinant. So the determinant is here. For cylindrical coordinate system, in terms of rho phi z, we have the determinant, and we shall substitute the values given in the problem here. 1 by rho. The determinant, first row is unit vectors rho, no change. Second row, partial derivatives, again no change. The third one, the values are given in the problem. H rho is 0, rho into H phi, that is 4 rho minus 2 rho square. This is given in the problem. Z component is also 0. Let us solve the determinant to find J. J now is equal to 1 by rho. Let us have a floor bracket. Too many brackets may appear. A cap rho component is given by multiplication of this minus this one. So it is 0 minus rho by rho z of 4 rho into rho square minus 2 rho cube. That makes the rho component. Now we shall go for phi component, that is this component, that is rho into a cap phi, which is given by the multiplication of these two terms and this one. So both of them are 0. Then lastly, we'll be having the z component, that is, so the multiplication of these two terms. That is going to be, first one is dou by dou rho of 4 rho square minus 2 rho cube minus the other term is 0. So this completes the first simplification level. Next, we'll carry out more simplification 1 by rho. Here, the differentiation is with respect to z. There is no z term at all. It's 0, 0. Here, differentiation is possible. So let us differentiate 4 rho square. 4 rho square is 8 rho. Minus 2 rho cube is 3 raised square into 2, 6 rho square. And last one is 0. So that is going to be a cap z term. So now further it is 8 minus 6 rho a cap z is Rj, the current density in ampere per meter square. So this is the answer for the first step. So we have found J in terms of rho. The question is to find current density as a function of rho. So there is a rho, it's a function of rho, but the direction is along z-axis, positive z-axis. Now we shall proceed to find the solution for part 2. So part 2 is to find the total current that is passing through a given surface. It is ds vector for a surface S. So surface integral of J is carried out in part A cap Z. So now we have to write an equation for ds. In the problem given that rho varies, Z is fixed at 0. So Z doesn't vary, then phi automatically by default it varies. Cylindrical coordinate system to define a circle. So ds is given by this equation. As I said already, any surface perpendicular to z-axis will be having unit vector a cap z. Here the surface is cylindrical. In cylindrical coordinate system, the surface perpendicular to z-axis is always a circle. It's always a circle. So this surface is defined by radius varying from 0 to 1 and angle 0 to 2 pi. So radius varies, pi varies, and rho is already there. So these kind of equations are already discussed in the introductory chapter of vector algebra. Now let us go for simplification. Az dot az is 1, so 8 minus 6 rho into d rho to d5. Let us separate the terms of similar kind. Now first the integration with rho, multiply the term with the bracket by this rho, that is 8 rho minus 6 rho square into do rho. So this is one integral. Second one is with respect to phi. Limits 0 to pi. This is here 0 to 1. So the integration 8 rho integration becomes 8 rho square by 2. Limits 0 to 1 for the first term. Second term, it is 6 rho cube by 3. Limits 0 to 1 into the last one is derivation of d phi is pi, that is 2 pi minus 0 is 2 pi. Height here. So this 8 is applicable only for this first term. It's not a common factor. So 8 into, so limits 1 square by 2 minus 0. This is the limit that is applied for first term. Similarly here 6 1 cube by 3 minus 0. Pi. So this is to be evaluated 1 by 2, so it is 4 minus 1 by 3, that is going to be 2 into 2 pi, totally 4 pi amperes. So now the current is 4 pi amperes. If you substitute pi equal to 3.14, I think you are going to get somewhere around 12.57 amps current. So that is the solution of this problem.